We're in section 12.5, and we're going to talk about line relationships in 3-space, or R3. So first of all, parallel lines have directional vectors that are proportional. So what that means is that you can represent one of the directional vectors for one of the lines as a constant, scalar constant, times the directional vector of the other line. If that doesn't occur, they're not parallel. Perpendicular lines is something we've already talked about, but just a reminder here that when we have this vector form of the equation of line in 3-space, that we can just take the dot product of the two directional vectors, and if it's equal to 0, that'll tell us that it's perpendicular. So just something to think about. In 2-space, or in 2D, when we have two perpendicular lines, they're going to intersect. What about in 3D? So just kind of thinking about this for a minute, remember that we can move around these vectors here, this v sub 1 and v sub 2. The vectors can move around. And so example to illustrate is a cube. And thinking about the diagonals that are illustrated here, they are orthogonal, but they don't intersect. They can intersect, but they don't have to. So just encouraging you to think about 3-space and how some things are similar, of course, with our 2D space, but to try to picture this in 3D, and some of your assumptions might not hold that did for 2D space. Intersecting lines share a point in common. That was something that, of course, happened in 2D. But we got an extra component here. We got the z direction. And so if we have 2 points on the if we have an intersection, then each of the x, y, and z coordinates have to be equal. Not good enough to get 2 out of 3, of course. Skew lines are non-parallel lines that don't intersect. And that's something that you can check by seeing where they intersect, assuming they intersect. And if you come up with a contradiction, then it means they're skew and they don't intersect. So we're going to do a problem that is sort of like, actually we can use this 13 too. Some of your suggested problems here, 13, 19, and 21. Determine if lines are parallel, skew, or intersecting. So here we're given the symmetric equations form of this, 2 lines. So let's address this parallel thing. If they're parallel, then we're done. They're parallel. Directional vectors would be a good thing to know from this. And so looking at the directional vectors of each of these, it's not too hard to obtain. For the first one, what we have, just a reminder here, in the symmetric equations, it's like we eliminated t, or we did eliminate t if we had done this work, and this is the result we got from the parametric equations. So to kind of backtrack here, what we're going to have for the x is x over 1 is equal to t, and of course we don't need that division by 1, and so on and so forth. So y minus 1 over negative 1, that's equal to t. So then what we'd have is y minus 1 equals negative t, and then we're going to have y is equal to negative t plus 1, so on and so forth here. And so for z, what we're going to get is 3t plus 2. So putting those together, we're going to be able to get our directional vector. So let's go ahead and do that. We have our vector, which we've been using r for, the xyz part, and then we have our r sub naught plus t times the directional vector v. So just kind of matching that up. What our v will be is the part that is next to the t. And so what we'll have here for v is 1 -1, and 3. So maybe you made this observation already, but if not, notice that with all that algebra, the denominators here is what turned out to be the directional vector. So a bit of a shortcut here we can do with our line 2 is we could just go ahead and make that observation and write it down. So I'll denote this one as v sub 1, v sub 2. Then matching them up, we're going to have 2, -2, 7. So now we need to compare. Perhaps v sub 1 is the one that maybe looks like it could be a constant scalar times v sub 1 to get v sub 2. So let's just kind of play the game that way, although either way is fine. So does v sub 2 equal a constant multiplier times v sub 1? And then I'm going to fill these in. So 2, -2, 7. V sub 1 is 1, -1, 3. So that constant for the first component here would have to be 2. So then you can just see if that holds down the line. Oops, I'm trying to show you the date and the time. So see, if that were 2, it would work for the first component. Actually, the second component as well, but it falls apart with the last one. We get 6, and it needs to be 7. So no, gotta have it work for all the way through. So they're not parallel. All right, what else do we have here? Skew or intersecting. So a good way to play this is assume they're intersecting. I'm going to kind of do this thing so I can get more on the page. Intersecting. So that would mean that all the x, y, and z components, or coordinates, I should say, are equal. We started writing out the parametric form of L1. And so this is our x sub 1, y sub 1, etc. So let's do the same kind of thing with L sub 2. Actually, write this out a little bit nicer too. So for L sub 1, in summary, what we had is x sub 1 equals t, y sub 1 was equal to negative t plus 1, and then z sub 1, or you can just leave it z, times 3t plus 2. Now doing this for L sub 2, I'm just going to do this in my head. I got these all equal to t, remember? So we're going to have x sub 2 equal to 2t plus 2. We're going to have y sub 2 equal to negative 2t plus 3. And we're going to have z sub 2 equal to 7t. Alrighty, so I just made a mistake. I was on autopilot with the t's. So we've only talked about using the parameter t. So let's talk about this for a minute. Now, when we have two lines that intersect, let's say they intersect, is that going to happen at the same parameter t for t equals 1, t equals 2, etc.? Probably not. I mean, in theory, it could happen, but not most of the time not, or that's certainly not something that has to occur. So let's imagine this line here, we had t sub 1 here, and let's say t sub 2 is actually where they intersect. So let's use a different parameter. Sometimes we use theta, but I'm going to use s here. So let's say we had s equals negative 1 here, and then it intersects at s equals 0 as the line is traced out. They'd still be intersecting even though these parameters are not the same. So we can't use the same parameter. We got to use different parameters when we set this up on our own. So let me correct my mistake. These are s's, not 5's. So backtrack. And of course I lose my other work. Redo that. So all right. Now, next thing. We're going to set the x components equal, y components equal, z components equal. So doing this, what we're going to get is our x coordinates equal. We have the equation, just going to really mark this up. We're putting these together, and we're going to have t is equal to 2s plus 2. Okay, what does that tell us? Not much. But together with another equation, maybe that'll tell us something. So I'm going to grab these equations, set them equal, and what I'll get from that is negative t plus 1 equal to negative 2s plus 3. So now we have a systems of equations, and we have another one coming, but we'll use that one to check, potentially, if it's consistent with the others. So I'm just going to use a substitution technique. We get t is equal to something in terms of s. So that's all set to go to plug in over here. So if I do that, I get 2s, I'm going to distribute a negative here, negative 2s minus 2 plus 1 equals negative 2s plus 3. Okay, so putting this together here, we have negative 2s, and then we're going to have minus 1 equals negative 2s plus 3. So when we try to get the s's together, we can add 2s to both sides, and we get something that's not consistent, actually. Negative 1 equals 3. No. So here we weren't able to reconcile these two solving for s. So what that means is that these equations this isn't a consistent system, and there's no solution. So just speaking to if you had picked a different component to deal with here, for example, the last two, or just kind of mixing these up in another combination, you might get a solution here for s and t, and then what you would do is you would check those with the other coordinates equation that you didn't do. Alrighty, so these lines we just showed are not intersecting. So at this point, when we've determined that our lines are not parallel and they're not intersecting, right there, that's the definition of being skew. So together, not intersecting, and not parallel, that together we can determine that the lines are skew. And that's it.